Okay, section 1.10, more on the C programming languages, characters, pointers, strings, floats, and functions. This is a lecture from section 1.10 of the book, An Introduction to Real-Time Computing for Mechanical Engineers, a lab-based approach that I wrote with Garbini and Devine. I'm Dr. Piccone, and MIT Press published it. That's the website where the book can be purchased from MIT Press, and rtcbook.org is the companion website for the book. Okay, let's get into it. In this section, we will cover more topics in C programming, topics that will be needed to write your code in the lab exercise. Okay, these are the topics that we'll cover: characters and casting, pointers and arrays, strings and pointer arrays, pointers and function arguments, floating point numbers, and variable argument lists. Characters and casting. A car is a single byte character. So this is the name given to this type. If one provides a character literal like, quote, A, end quote, the corresponding byte in memory holds a character code corresponding to A in the machine's character set, most commonly ASCII, which we went over in a previous lecture. Example, the 7-bit binary ASCII code for A is 10000001, as we saw previously. It is preferable, of course, to use string literals like, quote, A in C programming. We don't want to have to write out the ASCII code. However, we will occasionally need to manipulate character codes directly. Due to their integer nature, cars can be manipulated via integer arithmetic. For instance, if you initialize the variable x, you declare it to be a car, and you initialize it to the A character, and you declare y to be a character, then you add 3 to x, so 65 was the character code for A, and the decimal character code. If you add 3 to that, you'll get to 68, which corresponds to D. So you can do this integer arithmetic with characters in C. Type conversion, which is called casting. A C program tracks the data type of the memory contents corresponding to constants and variables. For instance, int x equals 65, x will be an integer. In memory, the integer value of x is just this. As we have just seen, this same character code can be used to represent the ASCII character A. The C program can be directed to reconsider the value of x as a character via implicit or explicit type conversion. Implicit conversion of the integer x into a character can be performed with the following variable assignment. So we have int x equals 65, char y. If we say y equals x, then y will be a character that is corresponding to ASCII code 65. Implicit conversions are performed in many ways, but the unifying theme is that an old expression is interpreted as some new type. Type conversion can also be explicitly performed with a cast operation, which forces an expression to be considered as a new type. So we do that by putting parentheses around the new type, whatever that is, int, char, etc., and then the expression, where new type is the new interpretation of the expression. For example, int x equals 65, our old friend, char y. We can say y equals, we can explicitly cast x as a character, which is interpreted as a character code. So this is implicit, this is explicit. Explicit Casting is usually preferred because it's easier to follow when you're reading someone else's code or your old code, as it often goes. Pointers and arrays. Pointers. A pointer is a variable that is assigned not a value, but a memory address. Okay. Pointers are key to writing efficient and clear C programs. To get the address of a variable y, one uses the address operator, which is the ampersand, as in ampersand y. To assign this to a pointer variable, the variable must be declared as a pointer to a specific data type. For an integer y, a pointer to it can be declared with int asterisk p and assigned with p equals ampersand y, or address. We'll often read this as address y. The pointer can be declared and initialized in the same line. So int p, so this is a pointer p, and we assign it to the address of y. To access the value to which a pointer points, the dereferencing operator, which is the asterisk, can be used as in asterisk p, dereference p. The table shows an example of a variable int y equals, so 0x is hexadecimal, 05, and a pointer p to it. So we've got the table with value in the first row. Second row is in terms of variable y, and then in terms of pointer p. So the address, which has this value here, so some hexadecimal address, we can write the address as ampersand y, or address of y. Or the address can be written just as p in terms of the pointer, p, because that's what the address of y was assigned to. If you want to look at the contents of the memory at this address, these are the contents. So it's 0x05, so hexadecimal 05. And in terms of variable y, we can just write y, right? That's the contents of memory that is named y. Or we can dereference p. So we can say go to the address, which p points to, and find the value, find the contents of it with the dereferencing operator, p. So that is how a pointer works. That's how you can declare a pointer. That's how you can get the address of a variable. That's how you can dereference a pointer and get the value of the address to which it points. Okay, so don't worry. If it's a little bit confusing now, you're going to get used to it because we're going to use it a lot. Pointer example. Assign the integer 8 to variable y and the address of y to pointer p. Print y, p, and the dereferenced pointer asterisk p. The following program performs the requested tasks. It requires stdio.h. Here is our main function, and we're going to declare an integer y and initialize it to the value of 8. We're going to declare a pointer p and initialize it to the value of the address of y. So now we've initialized an integer y and a pointer to y. We're going to print y is y. So we're just going to look at the value of y, which is always the contents of that variable. P is, now we're going to print a pointer. This formatted string has a pointer, %p, in it. So this format is for a pointer. D is for an integer. P is for a pointer. So we're going to print a pointer. P is the pointer. And we're also going to print the dereferenced p, which is to say the contents of the memory at the address that p points to. So we're going to dereference it, and that should be equal to y, right? We would expect it to be equal to y because that's where p is pointing. So the output should be something like y is 8, p is, and then this is just going to be some hexadecimal number that's the memory address, and dereferenced p is 8, which to say it's pointing at y. The pointer prints as a hexadecimal representation of the memory address that it points to, i.e. to the memory address of y. Pointers for arrays. Consider an array of length 10 declared by int z10. The array variable z behaves as a pointer to the first value in the array. There are some caveats there. We can say it behaves as a pointer. We probably shouldn't say that it is a pointer, as some people do, but it behaves as a pointer. For instance, let A be an array. So we're going to give it an array literal to initialize A, an array of integers. We're going to access the first value in the array with an index, so A of 0, and that returns 1. This value can also be accessed by dereferencing A, as in asterisk A, dereference A. Subsequent elements can also be accessed with dereferencing. So we can dereference A plus 1. We can dereference A plus 2, etc. That is, the value of A plus n is a pointer to the element with index n. This is a second way of accessing the values of arrays. So you can either use the bracket notation, or you can dereference pointers. Here is an example. Consider the variable declarations. Char x is this C character, and int y, so y is an array of integers with values 0, 1, and 2 as elements of the array. Create a pointer to x, a pointer to y, and a pointer to y of 1. So pointers to x and y are char xp is going to be a pointer by using the asterisk symbol, and we're going to initialize it to the address of x. So xp is a pointer to x, and yp is a pointer to y. Note that the address operator wasn't used for the array y because it's an array, and the name of an array acts as a pointer to the array. A pointer to y of 1 is, we can make a pointer to the 1 index element, which is the second element of y. The address operator is required here because y of 1 is a value in the array. Consider the following program. Int main, so we declare x to be a character, we declare y to be this array, just like we did a moment ago. We declare a pointer to x, xp, and we declare a pointer to y, yp, and we declare a pointer to the index 1 of y. We're going to print xp, and then we're going to print the dereferenced pointer xp. We're going to print yp, and then we're going to print the dereferenced yp. We're going to print y, and then dereferenced y. We're going to print yp1 and dereferenced yp1. So let's see what they look like. So xp, it's a pointer, so it's going to give a memory address here for where x lives in memory. And the dereferenced xp gives the character that we point to. Yp is a pointer to y, and y is stored at this memory address. Dereferencing that pointer, we get 0, which was the first element in the array, right? Y, and dereferencing y, gives us the same value. So we made a pointer to y, and it dereferenced in exactly the same way that dereferencing y worked. So this is to reiterate and to underline the fact that an array name acts as a pointer to the first element of the array. And yp1, which is a pointer to element with index 1, which is the second element in the array. If we look at the address, it's one element further, a 32-bit increment here. And we get yp1 dereferenced equals 1, which is this one element. Note that the array y acts just like its pointer yp, so we treat an array identifier as a pointer to the array. Another array example. Problem. Initialize a character array with characters A, B, and C, loop through the array, and print each character without using array subscripts. So the bracket notation. Solution. The following program satisfies the requirement. It requires stdio.h for the printf function. So int I, declare I to be an integer, declare x to be an array of characters, and initialize it to A, B, and C. Int xn equals size of x, which is the number of bytes in the array. For I equals 0 through 1 less than the number of bytes in the array, and with increments of 1 in I. So for each byte, we're going to print x of the index I, and then we're going to print is, and we're going to dereference x plus the index with the dereferencing operator. So the result is x of 0 is A, x of 1 is B, and x of 2 is C. Although we printed it with the brackets, which was used to denote that this is the first element, second element, and the third element of the array, we didn't use that notation for determining what the element was. We instead dereferenced a pointer, which is the other way to access elements of an array. So this is our result. We got out each 1 byte character. Remember, characters are 1 byte. So using the size of function is very convenient when you have an array of characters. It is also the length of the array. We have used the fact that a char is guaranteed to be stored in a single byte of memory. The size of function is a built-in C function that returns the number of bytes in an array. In general, to determine the number of elements in an array, one should divide this by the number of bytes per element. Of course, in this case, that's just 1. The for loop adds the loop index I to the array x, treating it as a pointer. Then dereferences this new address. Again, we have assumed that each element in the array is a single byte, and therefore it has a single address. Strings and pointer arrays. A string is a sequence of characters, as in the string literal real. Note the double quotes instead of the single quotes that we used for characters. In C, a string is stored as a character array with the last element with this escape 0, which is called the null character, which corresponds to the null ASCII character. In memory, this looks like any other array. It has characters R, E, A, L, and then the null character. They're stored in consecutive bytes in memory. A string can be declared and assigned to a variable with char, dereferencing operator s, equals, double quotes around the string real. String literals can be concatenated at compile time as the following pattern shows. So if we do char dereferencing s equals quotes and then a space in between or other white space in between, these will concatenate at compile time, meaning it won't be concatenated during the run of the program, but when the program is compiled. A very common need is the storage of multiple strings in an array. One way to do this is to create a two-dimensional character array. A multi-dimensional array requires the allocation of a fixed block of memory with a fixed size. In many cases, this is not ideal for storing strings because the lengths of the strings may vary. The preferred solution is to create an array of pointers to strings. Each string is given its own block of memory corresponding to its actual size. When the strings are known at compile time, they can be given as literals like this: real-time computing. Those are the 3 strings that we're going to put in an array of strings. The strings are given their own memory addresses, which are stored in SA. Consider the verse of the intrepid Antigone. Be brave, you are alive, but my life has died, already for the sake of helping the dead. We would like to inspire the youth by printing this to the console. For effect, we would like to repeat the imperative, be brave, 3 times, before and after the verse itself. Write a program for this noble task with minimal memory usage and a pointer array for string storage. Okay, consider the following program. Here's our main. We're going to have an integer I, a character array that is be brave, and then the next element in the array is you are alive, but my life has died, and then the third element in the array is already for the sake of helping the dead. So those are our 3 strings in our array. So we're going to loop through 7 times because we want to print 7 things. We want to print be brave 3 times in a row. Then we want to print the entire verse. Then we want to print be brave again 3 times. So most of the times through here, we're going to just print the first line, which is be brave. And SA of 0 is going to give us the first element in the array. And we're going to print it as a string. This formatted string here with the %s gives us a string to insert. And we're just going to print it. Okay, so the first 3 times, that's the only thing that happens. I will be equal to 0, 1, 2, in which case we're going to print, and then we're going to printf new line. So we'll do be brave, new line, be brave, new line, be brave, new line. Then if I equals 3, so this is our one special case, we're going to print the whole thing. So we already printed the first line, so let's also print the second line and the third line, and then give us a new line, and then again for I equals 4, 5, and 6, we're just going to print the first line, be brave, and the new line. So that is our function, and we get the output that we looked for. Be brave, be brave, be brave, and then the whole verse, and then the repetition of be brave at the end. Pointers and function arguments. Arguments are passed to a function by value, which is to say assigned to temporary variables inside the function. These variables are callable only from within the function. An effect of this is that a variable v passed to the function foo, i.e. foo of v, cannot be altered by foo. So inside of foo, we can't alter the variable v that's outside of foo. However, the altering of a function's argument is often an efficient or memory optimal strategy. Whenever we want to alter a function's argument v, we pass the memory address of v via the pointer address v, or ampersand v, i.e. foo of ampersand v, and then of course we have to write foo to expect a pointer as its argument and not a value. We could dereference that pointer inside to find the value of v, and then we can assign to that pointer's address inside of foo. For example, king me. Consider a program for playing digital checkers. At certain moments of the game, a given game piece is eligible to be converted to a king. At such moments, the player might exclaim, "King me." Suppose that the king state of each of the 24 game pieces are being stored in an array int a24, with a value of 1 signifying that it is a king and 0 signifying otherwise. write a function kingme, which takes 2 arguments, an address and an integer, that kings piece I of the original array A. Write a main function to test kingme. So here is our program. Also requires stdio, but main, we've got integer I, we've got array A, which is initialized to zeros. We loop through half the pieces, so I equals 0 through I equals 11, and we're going to increment I by 1 on each pass. So we're going to king the first 12 of these pieces. They all started off with 0. We want to make all of them 1. So we're going to print piece, and we're going to print the index, and we're going to print the value of A at that index. So piece I was A of I. Then we're going to king that particular checker piece. So king, we're going to give it the array A, and then I, apply, kingme. And then we're going to print now and then we're going to print the current value of A of I. So we're going to change A of I in the process. Kingme then is going to have as its first argument a pointer B to the array, and J is an index. So B of J is equal to 1. So how are we able to do this? How are we able to take B and assign 1 to that? Because this array A, notice we pass it without the address because it's an array, so it acts as a pointer. So A is a pointer. We pass A in here, we treat it as a pointer, and then we say, oh, okay, well, the jth element we're going to set to 1, and then we're going to return 0. So that is a simple function to turn any index of an array to 1. So the output that we printed to the console is piece 0 was 0, now it's 1. Piece 1 was 0, now it's 1. Piece 11 was 0, now it's 1. So all the way down to 11. And yeah, so we were able to turn the zeros for the first 12 elements of A to 1s, signifying that they are now kings. Okay, floating point numbers. Floating point numbers come in 2 varieties in C. Float, or single precision, are often 32 bits. It's actually system dependent. And then double precision, often 64 bits. But the definition requires that double be double the precision of float. A double uses twice as many bits as float depending on the platform. A 32-bit float can represent floating point numbers in the approximate ranges for positive numbers 10 to the negative 38 to 10 to the positive 38, and negative numbers from negative 10 to the 38 to negative 10 to the negative 38, with a precision of 6 decimal places. A typical double has approximate ranges positive from 10 to the negative 308 to 10 to the 308, and negative 10 to the 308 to negative 10 to the negative 308, with a precision of 15 decimal places, so more decimal places. A double literal can be written like 3.14, as we would normally write out a decimal number or a regular decimal number. To write a float literal, an F should be appended, 3.14F. That is, C assumes that a regular decimal number, like 3.14, is a double. So when you write a literal 3.14, you're making a double literal, unless you put an F at the end to signify that it is supposed to be a float. Promotion. Some compilers have options to treat regular decimal numbers as floats. For instance, the GNU compiler collection GCC compiler has the option F single precision constant that can be used for that purpose. With the W double promotion option, GCC can also warn when a float is implicitly promoted to a double in an expression. Finally, variable argument list macros. Some functions accept a variable number of arguments, like foo of A and foo of A, comma B, comma C. So the same function foo can take a single argument or it could take multiple arguments, and this would be a variable number of arguments if it was, in fact, able to do that. Argument parsing. The C standard library header stdarg.h includes a facility for handling variable arguments, provided as 4 macros: va start, va end, va arg, and va copy, and a special type va list. VA for variable argument. The type VA list is used to declare the argument list variable, conventionally AP for argument pointer. A variable argument list definition might start as voids being the return type foo, int x, comma, and then we get ... And then we start our function. And the first statement in the function is VA list AP. The ellipsis stands for the unnamed arguments. So this ellipsis, it's not just, oh, something would go here. It is in fact the syntax required for a variable number of arguments. Okay, now AP can point to the variable length list of arguments provided the function. We declared AP to be that variable length list of arguments. The macro va start grants access to the argument list by pointing AP to the first unnamed argument. Its prototype is void va start va list AP param n. The first argument is the declared va list AP from before, and the second argument param n is the last argument declared in the function before the unnamed arguments. In the previous case, va start AP, comma x is to begin the argument handling. Okay, let's see how to use that now. Now the game is afoot, and we can do something similar with the arguments by following the pointer AP. Often the macro va arg can be helpful here. Its prototype is return type va arg, va list AP, comma type. Type here is any data type like int, char, etc. The macro va arg will parse the currently pointed to argument by the provided type, increment the argument pointer AP address, and return the parsed argument. It can be called in succession to parse each unnamed argument. For instance, if there are 2 unnamed arguments, a char and a double, after va start, one could parse the arguments with char a equals va arg AP char, where we say a is going to be a character, and double b, and we're going to say this argument is going to be a double. So the second argument is going to be a double. Once va start has been evoked, the function must not return before calling macro va end, which performs some cleanup. It takes one argument, the current argument pointer, so va end AP is the usual call. It is important to note that there is no facility here for determining the number of arguments passed, so one must encode this information in some way. A common method is to make one of the named arguments represent the number of past unnamed arguments, as we will see in the following example. So here's our variable argument list macros example. Write a function sum to sum a variable number of integer arguments. Consider the following program. So we're going to declare a prototype for sum, at the top, and then we've got our main that essentially just calls sum on 4 arguments, 3, 8, -11, and 10. And the idea is that we want to sum those up and return it to s. So we just need to write sum now. So sum is, first argument is n summands. How many variable arguments are about to follow here? So 3 in the example is how many are going to follow. So this is the one named argument. And then after that, we have the variable number of unnamed arguments. Okay, we start off by declaring the arg pointer. So AP for argument pointer. We have I, an integer, s being initialized to 0. This is going to be the sum variable. Okay, VA start. We're going to start our argument parsing. So now we're going to do a loop. And in order to know when to stop, this is where our one named argument, n summands, is going to come in handy. So we're going to say n summands time, starting at 0, going to n summands minus 1 for I, increments of 1. We are going to take s, which started off at 0, and we're going to say s equals s plus VA arg of AP, and interpret what AP points to as an integer. So parse it and then sum it up with our existing s and replace the current value of s with the new sum. So loop through 3 times in the example here. And then after that, end our argument parsing with VA end, AP. So our sum is already computed. So let's go ahead and return it. And this should print the sum is 8 minus 11 plus 10 is 7. So compiling and running the program results in the sum is 7 being printed. Variable argument parsing will be required for a function written in lab exercise 1 at the end of this chapter. So that's why we had to go through it at this point in time. And now we've learned some more of the C programming language. You're getting enough to write some more interesting programs, and you're going to get some experience doing so in lab exercise 1. Okay, only a little bit more to go over before we go over lab exercise 1. Okay, see you next time.